has been started.
Good morning, everyone. My name is Corey Carlson. I am with URETEK Holdings. Thank you very much for joining us today for our webinar. Today we are very excited to have a special guest, Dr. Jim Tinjum. He is a professor with the University of Wisconsin, and they currently have a study underway where they are utilizing URETEK 486, which is a chemical grout that we use day in, day out in a variety of different applications, which we'll talk about very briefly. But the rail study that Dr. Tinjum and his team are conducting is showing that chemical grout used for rail injecting into the existing ballast is actually performing better than brand new ballast. So very exciting study, and it's underway, and so Dr. Jim will give us an update on what that study looks like. But before we go into that, I'd like to speak for about 10 minutes to give you kind of an overview of URETEK Holdings, but also the URETEK 486 products, some of the product characteristics, so you'll have a little bit of background going into the portion shared with us with Dr. Tinjum. This is a webinar, so many of you have participated in them before, but we will mute all lines during the webinar, and you can click the raise your hand icon, type in your questions, and we will address them at the end. There will be 1 PDH credit available for today, and after this webinar you'll receive an email survey. If you could please fill out the survey, let us know how we can improve, how we can make these webinars more useful to you and your team, as well as that will be how you will let us know that you do in fact need a PDH. Who is URETEK Holdings? We are a contractor that is headquartered in Florida, but we're unique from other contractors in the fact that we are going after valued engineered solutions, some of which are proprietary, some are not. But in doing so, we utilize sales engineers throughout our 31-state territory. We also do webinars such as this to bring awareness to the different types of solutions that we have, where we'll be using the chemical grout instead of a conventional solution of cementitious grout, or relining pipe using Centra pipe instead of a remove replace. So we are a contractor that also values safety. We have a very low EMR of 0.75, also the applicable insurance and bonding necessary. And then we focus on a variety of end markets, from infrastructure, which we'll talk about briefly today, commercial, whether it is lifting slabs, increasing bearing capacity underneath the footing, as well as residential homes and pools. For the last few months, we've been really focused on an outside-inside approach to help repair our aging infrastructure. And for the inside of the structure, we are an applicator for Centra pipe, where that is the process of applying a concrete in 1/2-inch lifts. And we can do that to manholes or to lateral lines. As you can see the picture on the left, we will pour a 12,000 psi flowable fill in the invert, and then the picture on the right shows our spin caster, where it will be applying the concrete in 1/2-inch lifts, so giving a like new solution on the inside. Now on the outside of the structure, we utilize the URETEK 486 chemical grout that we'll be talking about here in just a minute with Dr. Tinjum, because it is the same chemical grout that they are using for their rail study. So as you can see by this picture, our chemical grout, represented by the yellow, is filling the voids around the infrastructure. It displaces the unwanted water, and then it also encapsulates the soil, improving that bearing capacity. So for our outside-inside solution, we are treating the inside of our infrastructure as well as the outside. Here's a real-world application where we did in Florida. You can see the center picture shows the material being injected from the road surface, and it will be injected on both sides of the pipe. The picture on the right shows how that material injected from that road surface will follow the path of least resistance, displacing the water, filling the voids, densifying the soil, and then you can see that outcropping that has surfaced at the grass. We'll remove that. Another item of note, particular of this project, was it is a natural spring and a manatee migration location. So our material is very environmentally friendly, where we can in fact work in manatee locations as well as blue waters for the Corps of Engineers and any other environmentally sensitive areas. So for those on this webinar who are not familiar with URETEK 486 or chemical grout, the question is, well, what is chemical grout? So I'd like to give a little background before hand over the webinar to Dr. Tinjum. Chemical grout is not necessarily new. It's been around for over 25 years, over 85,000 different applications. Those applications can range from DOTs on highways and interstates to residential properties, as well as infrastructure and commercial. So a lot of various applications, and definitely a proven technology. We have a very precise monitoring process, and we do this for a couple of reasons. With the expansive forces of the chemical grout, it can expand 20 to 25 times its original volume. And in some projects, we want to get lift. So we have worked on rail lines where we have wanted to raise the rail track 1 to 2 inches. So we'll set up survey equipment to make sure that we are raising the rail to that desired elevation. There are also situations where we do not want to raise. We're just trying to densify the soil and fill the voids. In those situations, we still set up the survey equipment, but we are making sure that there is no movement at the surface. So it's a very precise process. Also, some of the process, we will utilize a patented process, but we also have non-patented processes, depending on what we are trying to achieve. As I mentioned, it is a heavily monitored process, and we're able to do that because the polymer can achieve its 90% strength in less than 15 minutes. So this is a very fast process with minimal cure time that we can achieve many of our projects in a timely manner, sometimes days. Because of that fast process, we also work on live rail. So there have been projects, whether it's we've worked for Amtrak, we've worked for Norfolk Southern, CSX, a variety of different rail lines that we've worked on throughout the country, where we will work on live rail lines because of that fast cure time and the fact that it hits its high strength in 15 minutes. A few last items to share is another benefit. It has a very high strength to a low weight. This is very advantageous, especially as we talk about rail and the aging infrastructure. Underneath rail lines and that bedding material can be older storm sewers. So that aging infrastructure, it is a conventional solution to be putting that cementitious grout on top of that already deteriorated load. You're now putting a heavier dead load on top of the deteriorated ballast or aggregate. And so with chemical grout, we are able to achieve the same results, but yet using a lightweight material. This product is also hydro-insensitive. It is a closed cell material, so as it expands, it displaces the water. So any situation where you have water that is not desired, by using the chemical grout, it will displace that unwanted water and is not a concern from a quality perspective as it is curing. As I mentioned earlier with that manatee example, our product is very environmentally friendly. It is NSF 61 certified and can be used on all types of different environmental projects. So talking about the end market for rail, why did we choose to do a rail webinar this month? And really the reason why is all of us on this webinar are shareholders to one capacity or another. A lot of rail is owned either by private companies or even public entities. And so as we as civil engineers or geotechs are involved in really providing the best solution for that end shareholder. And as the U.S. rail infrastructure continues to age, we need to come up with better solutions to repair. And what's exciting about this study, we'll hand it over to Dr. Tinjum now with the University of Wisconsin, is this study is showing that a rehabilitation process with chemical grout is actually performing better than your traditional brand new ballast. So with that being said, I'd like to hand it over to Dr. Tinjum right now. And we are very honored to have Dr. Tinjum. One, it's a school year right now, and so he's very, very busy with classes and all the activity he has. So thank you for taking the time out of your day to speak to all of us and to share your report.
Well, good morning, and thanks for that introduction. And I apologize right out in front about the very long title, but as we say in the research industry, you get about $10,000 in grant money for every word in your title. So thus, I definitely wanted to, at least 10, 12 words in our title. I do want to acknowledge our base funding supporter for this project and the predecessor projects. It is the CFIRE, which is the National Center for Freight and Infrastructure Research and Education, which is based here out of the University of Wisconsin-Madison. And thank you for their contributions for the past 3, 4, 5 years on this rail project. Also like to thank many of the contributing students that you see on the screen, and my colleagues, Professor Tuncer Edel and Dante Frada, my colleagues here at the University of Wisconsin. So today, over the next 40 minutes or so, I'm going to be talking about a progression of topics, starting out with some rail engineering 101 as far as perspective and impact to set the stage for what we're trying to achieve as far as our objectives. Because this is a new application of a product that has been around, we do want to present those scientific underpinnings about what improvements in the mechanical properties of polyurethane stabilized ballast will get us, but recognizing that those are in lab scale, even though some of our lab experiments are quite large, ultimately then leading into our field demonstration site that we are working on right now to achieve possibly with injection this upcoming spring. So some perspective. So as an example, here in Wisconsin, the frac or industrial sand industry is a big deal, and also in northern Illinois and in southwestern Minnesota, the industrial sand that's been largely used in the past half a decade for fracking the oil and natural gas fields across the country. In shipping this along with other heavy industrial products really is pounding our rail industry above and beyond what it's been experienced in the past. So with respect to the fracking industry, we have loads of sand heading out to the oil fields, Texas or North Dakota, Ohio, Pennsylvania, and then a lot of that oil heading back to markets, whether that be in Minneapolis, Chicago, or down in the Gulf Coast. So the rail industry is experiencing a lot of demand of a lot of very heavy loads. So I want to start to see what does the impact of those heavy axle loads do to the performance and maintenance requirements for a typical rail system. So the big picture is here we are looking at a schematic of the oil and gas fields across the United States that have been heavily utilized over the last decade or so for this new industry. And the perspective is much of that industrial sand that's used as the proppant for enhanced recovery in these fields are being shipped from primarily northern Illinois, Wisconsin, southwest Minnesota, a little bit in Iowa. So we are sending out large shipments of industrial sand, and as we had seen in that previous image, a lot of that oil is coming back on those same rail lines. So big picture is the infrastructure for rail is across the country, and it's being used at very intensive applications, both as far as load, tonnage, cyclic use, and that's a perspective of why we are considering extending this stabilization product to the rail industry. Okay, so with transportation of heavy loads, we're going to call them HAL for the rest of the next 3 or 4 slides here. Is a couple of things that we're concerned with is number one is those heavy axle loads do stress the substructure of the rail, including the ballast, the subballast, and the subgrade. And those heavy loads will accumulate strain underneath the system. At some point, there'll be too much vertical plastic deformation where a leveling or cleaning or some other maintenance activity will be required to maintain the track geometry and alignment. So, we look at these heavy loads, and I'm going to go to this next image, which is actually a video. And I understand that the webinar platform, the video may come across sketchy, so I'm just going to try it. And if you can't see it very well, in about 20 seconds, I'm going to explain what we are seeing. So just in case that video did not come across clearly, what you saw are train cars that had 225,000 pound load, and what they were doing, even on a fairly good ballasted track section, you saw quite a bit of elastic deformation in both those rail ties and those sleepers. Basically means is that the substructure is taking a lot of stress, and that's a dynamic stress, and the ballast and subballast is moving in response to those loads. There are 2 issues with that cyclic displacement. Number one, that dynamic displacement caused premature aging or fouling of that ballast substructure. As the ballast particles, say 2-3 inches in diameter, rub against each other, the edges start to break off, and as those edges breaks off, the track becomes a little more fine-grained, and that extra fine-grained material retains moisture. For those of you that are civil and geotechnical engineers in the audience, moisture retention is quite bad for the structural capabilities of the system, and the strength of the system goes down with that increased moisture retention. So a little bit of a background for those of you that may be new to the rail industry. A typical section of the substructure of a track system includes going down from top to bottom the rail, a fastening system to the tie, Generally, the upper foot or maybe even more is going to have hopefully a clean ballast material. What I mean by clean is a material that has limited fines, good edges to them, and has high strength and capacity to resist those loads. With much of the United States infrastructure for rail being out there for, we're working on tracks that have been there for 120 years. There's going to be sub-ballast below that, either for new construction or the sub-ballast that 20, 30, 40 years ago used to be the main ballast section, and as maintenance activities occur over the years, new ballast is placed on top and the sub-ballast just becomes lower into the system. This is important to keep in mind because the sub-ballast is very much a target of our interest and our research because that sub-ballast is going to be degraded, it's going to have fines in it, and it's going to be apt to maintain moisture, retain moisture, and thus not structurally transfer the load as well as we would like. Underneath then, compacted subgrade and natural subgrade need to also recognize that some projects, that is where we would be looking for stabilization, especially if that natural subgrade is organic, soft, wet, or any nature of that just can't take the loads from that above system. So a problem statement is that this ballast layer deteriorates under numerous loading repetitions. This deterioration in the substructure leads to eventually permanent deformation in the track. That permanent deformation is what we call plastic strain, or the permanent accumulation of strain due to that loading. With enough plastic deformation, the geometry may be compromised, and we threaten the rail operations at a minimum. Often there will be speed limits posted to rail sections that have geometry issues where we just have to run the trains much slower than operations would like. And worst case situation, derailments that unfortunately we've seen time and again in the news over the past years. So our objective with this research is to prevent track deformation, to enhance the rail operations, and really ultimately our goal is to provide a system where we do not need to do as much maintenance and or decrease those maintenance frequencies to something that is more economically beneficial, and also such that we don't take rail sections out of service any more than necessary over their lifespan. So I'm going to play one more video. I'm going to leave it go for about 20 seconds, and then again, if the video did not come across well on our webinar platform, I'll just describe what we are seeing here. So what we saw here was a video from a recent trail derailment here in Wisconsin. And when I say recent, I mean this weekend. We actually had 2 trains derail here in Wisconsin over this past weekend. One carrying oil and the other carrying ethanol. Fortunately, the rail cars carrying the oil were of the new design, the new structural design, and there was no significant leaks in the system. In the other derailment, one of the rail tankers carrying ethanol did puncture, and that car did unleash its load of ethanol. So it's too early to understand what caused this particular derailment, but I just want to indicate that ultimately what we're trying to do is ensure a safe product that can help the rail industry in remediating and maintaining certain sections of the track that may have unsatisfactory performance. So now, going into what we're doing here at the University of Wisconsin, I want to show, without going into too much detail, but show you some pretty pictures and graphics. What we're trying to do from the science basis is to demonstrate the improvements in the geotechnical/mechanical properties of polyurethane stabilized ballast, sub-ballast, and the like, so that we have an indication of what we would expect to see in the field before we carry out larger field-scale operations, which is the next step in this process. So as an example, here we're seeing a fairly unique cyclic loading machine. There's only a handful of these in the United States. We were one of the first universities to have this large-scale cyclic triaxial device. University of Illinois also has one. And because of the size of the ballast, we need a very large loading platform, actuator, and the like. So we're testing very large systems such that we can get the properties of rail ballast and fault rail ballast. We are looking at applying those loads in two manners. Is number one, such that they represent accurate and reasonable in situ confining and vertical stresses, and also so that we apply cyclic dynamic loads in a hertz frequency that is representative of whatever speed of train we want to replicate. So in short, is what we can do is simulate the loads underneath that sleeper or tie, confining pressure, cyclic frequency, and the like, and we can run 2 or 3 years worth of traffic loading in a matter of 24 or 30 hours here in our laboratory. So I'm going to give you some results here for about the next 10 minutes, and then the final 10-15 minutes of the seminar, I'd like to talk about the polyurethane stabilized ballast to enhance these deficiencies that you're going to see in these upcoming slides. So first, heavy axle loads is what you see in the graphs in front of you, is an indication that, not an indication, these are actual research results, that the heavier the load of the car, the more plastic strain accumulation occurs. So makes sense, but the degree of increase is quite interesting. So on the left, we have clean recycled ballast going from, on the bottom, 250 kPa, which would be equivalent to a 195,000 pound train car. We don't have most of the train loads in the U.S., at least here in Wisconsin, are somewhere between, say, 200 and 270 kips. A lot of that is because of the limits on the rail bridges. Often the loads on train systems and networks is controlled by the capacity of the bridges, which are very expensive to replace and modernize. So first thing is we need to be aware of is that the heavier the load, the larger the accumulating deformations are going to be. So once that plastic deformation occurs at some point, the rail industry is going to go in there, the rail owner is going to go in there and do some form of track maintenance, whether that be something as simple as track re-leveling, to going in there and cleaning out some of the fines and placing some new replacement ballast. It's a little bit old data, but it's the best I have for Class 1 freight rail in the United States from that data from 15 years ago. Maintenance of ballast is about a $500 million per year operation, probably closer to $1 billion and more now. I know through colleagues in some Class 1 rails that I am familiar with, one company that I will not name spends $200 million themselves on ballast maintenance across their infrastructure. What happens over the life cycle of a ballast section is we start with clean, controlled, engineered ballast. It generally starts to accumulate smaller fine particles, either from degradation of the particles themselves and or intrusion from environmental conditions outside, such as wind-blown silt, spillage from the themselves, or pumping of fine-grained material up from the subgrade. So at some point, you're going to get heavily fouled ballast is where the void structure is completely filled with the finer materials and the moisture, and that strength of the fines control the strength of the ballast, not the larger particles themselves. So as this fouling level increases, the service life of the track deteriorates and decreases. What is the impact of ballast fouling? Well, this is an example of a graph where we place fines in a clean ballast, and fines are defined by Cyclic as the percentage passing the number 4 sieve plus the percentage passing the number 200 sieve. That is called the fouling index, and you'll see the highly fouled ballast deteriorates much more quickly, exponentially, than a cleaner ballast. In this graph here you see is that the moisture was controlled at 15%. So increase the fines, the rate of cumulative plastic strain accumulation increases. This graph that we're looking at now shows the impact of increasing the moisture content. In this particular graph, we have coal fouling or coal dust fouling at a Fi equals 24%. And you see as we increase the retained moisture going from 3% to 14%, you also get that exponential increase in cumulative plastic strain as moisture is added to the system. So in summary, damage to the rail system comes from many varieties. Number one is the loads themselves, and heavier or heavy axle loads will increase the damage more than lesser loaded cars. 2, the higher the fouling index, the higher the plastic strain. And 3, the higher the retained moisture, the higher the permanent deformation of the ballast system. Types of fouling that we've investigated through the years are coal fouling, mineral fouling, which basically means that the ballast itself deteriorates and the edges break off, and that edges is the fine material, clay fouling, and frac sand fouling, which we have a particular interest here in Wisconsin because of the concentration of industrial sand mines here in our region. So with that, we were looking to see what we could do to enhance the performance of freight rail ballasted sections, mitigating the impacts of subballast that's already been followed, and or to go in and stabilize track sections that may have geometrical issues. So thus our partnership with URETEK, and like to thank one of their best technicians, Steve Reed, for coming up to Madison several times, and Dr. Randy Brown for their insistence in this industrial academic partnership. So what is polyurethane stabilized ballast? And so what it is a chemical grout that was discussed earlier, in which is injected into that ballast or subballast system, and basically it takes up the void space. As far as a phase diagram, you see that the polyurethane product itself may be about 7% of the overall volume. That can give you an indication of the chemical costs and application costs for this material. Look at it up in the lower right corner. You just kind of see that honeycomb structure of rigid polyurethane foam. That's what it looks like under the microscope, and we saw cut open a ballasted section in the upper right corner to give you an indication of what this looks like. So what type of mechanical properties are we dealing with? And so I'm going to take you through fairly quickly some of the information that we have here at the University of Wisconsin to use as base mechanical property input for anybody that's interested in how much of an improvement there is. So we have data and published data on compressive strength, resilient modulus, and also because there's many ways to apply the polyurethane stabilized material into the ballast, also flexural fatigue and strength. So we have evaluated in the laboratory here over the past 5 years fatigue, stiffness, and strength, all of those engineering properties that are necessary to scientifically understand the process, and then thus the benefits coming out. What we do is we've got ballast that's coming from various of our rail partners here in the area and national rail companies. We have both clean granite, rhyolite type ballast, dolomitic type ballast, a variety of ballast types as far as quality of the ballast and the gradation of that ballast. We put those into molds, fairly large molds, and then we do injections here in the laboratory for beams and columns to test the material. And just as an example, the unconfined compressive strength is just achieved by applying a load, measuring the deformation of that load or that axial strain here, and that peak strength would be called the unconfined compressive strength. In this first graph, you're going to see, okay, so how does it improve the compressive strength of the treated ballast section? What you're seeing in this graph is that clean ballast is going to have compressive strength on the order of 500 to no more than 1,000 kPa. And I apologize for the SI units for some of you that are still hoping everything was in PSF. We are a university, and most of our research is published in the SI. So, but relative to that, the scale, you see that the polyurethane stabilized ballast is significantly stronger than clean ballast, but well less so than concrete. This is a very important graph for two reasons. Number one, the strength increases over clean ballast. However, as far as replacement or rippability, it's not like it's concrete. So the theory is that material could be ripped or tined out of the substructure if necessary for future repair. Cyclic and monotonic beam testing. So beam, so we have 3-point beam tests, and this more goes to the flexural strength and that repeated dynamic loads to the system. Those have been measured. Flexural strength tests will get at either failure or at some point in failure of the breaking strength to get the flexural parameters of the polyurethane stabilized ballast. Flexural fatigue, how many cycles it takes to fail the material, also goes to the longevity of the material. And then cyclic triaxial compression testing so that we can get that accumulative plastic deformation behavior, also while measuring the elastic deformation. Just some images of the unconfined compressive strength testing and flexural beam test specimens that we have tested here in our laboratory. And I'm going to spend a few minutes on this graph right here because this is roughly the outcome of this. Ultimately, in a rail substructure system, we are interested in is how much deformation has occurred through a representative section, and we measure that as the cumulative plastic strain. Now, the FRA generally recommends maintenance at some level. I believe it's 2.5%. I might be wrong right there, but going to go through this for perspective. This is all for specimens that were tested for 200,000 loading repetitions. So on the far left, you'll see the blue colored on the left, is that is fouled ballast with a moisture content of 15%. The following is only 5%, so it's not huge. The clean ballast in the green, the middle line, is for your reference. And then finally, the polyurethane stabilized clean ballast, as you see the scale of how much plastic strain accumulation occurs over 200,000 cycles. Now, going to the right, if we increase the stress on the track, such as heavier axle loads, you'll see that the cumulative plastic deformation for clean ballast gradually increases to above 1% with 400 kPa deviator stress. But you'll see that polyurethane stabilized recycled ballast and polyurethane stabilized fouled ballast in the middle here, in the area of 350 deviator stress, is what shows is that when we stabilize fouled ballast, the cumulative plastic strain is well controlled and managed. So two things from this graph is, number one, stabilized ballast is stronger than clean ballast, and secondly, stabilized fouled ballast also is well behaved as far as cumulative plastic strain with this product. In some materials, this should show the polyurethane stabilized ballast in comparison to rigid polyurethane foam in and of itself and ballast. What you're seeing here is that in addition to the compressive strength, we also increase the flexural strength because clean ballast does not have flexural strength because that's a granular product without adhesion or cohesion. So we are also increasing the flexural strength, and then going to the right, or excuse me, just more material as far as the elastic modulus, which is just an indication of the repetitious loads to that material as a residuant modulus. So in summary, before we go to our upcoming field project, polyurethane stabilized ballast, as measured by plastic deformational behavior, is better controlled than clean ballast, recycled ballast, and definitely fouled ballast. We can stabilize fouled ballast depending on the type of material that it's fouled with. And even though polyurethane stabilized ballast has elastic moduli that's typically less than ballast, that just means that we have recoverable strain, or elastic strain does occur in the material, but the cumulative plastic strain does not manifest. So that's actually a good thing as far as a property. So we have demonstrated in the laboratory the feasibility of using a chemical stabilization approach in track substructure. That stabilization does not have a negative impact on the elastic response. Injection methods are feasible for track stabilization, and PSV can greatly increase the track mechanistic life cycle. Now, I'm just going to go for about 3 more minutes. I want to leave about 10 minutes for questions, so largely on track here.
Dr. Tinjum?
Yes.
If I can just hold one moment, I just wanted to mention to the audience real quick, this is Robert Armstead, that if you do have any questions, there's a questions section within the webinar tool, or you can ask them directly through the message bar. After you raise your hand, I'll question you. But if you have some questions as you're thinking through, go ahead and submit them now, so in 10 minutes we've got a good hopper of all your questions. So, thank you for the interruption. Sorry about that.
No problem. Again, because of the emphasis of the mining and processing of industrial sand here in the upper Midwest, this is what we're interested in as a field site. Across Wisconsin, Minnesota, Northern Illinois, there's lots of intensive capital projects to serve these markets. And the other interesting thing is that especially close to the source, we do tend to get a lot of spillage from the frac sand that does go into the ballast and retain moisture and otherwise have deleterious impacts to that structure. So just as an example, for an unnamed railroad somewhere in the United States, now, we may have problem areas with lateral displacement that we'll have concerns about for stabilization approach. To the left, you see that the retention system is not capable. You have to build very strong structural systems to retain those lateral forces, and another image to the right about what the lateral forces can do to your track substructure. In addition to vertical alignment issues where you'll have to go in repeatedly for vertical leveling to maintain that grade. So these are some of the areas that we are interested in. We'll point out that our technology was, not our technology, our partner's technology, and we're demonstrating that technology, was highlighted in a recent issue of Civil Engineering magazine, the September issue, if you want to go back, looking at just what this remediation looks like and what we are seeing. So a very quick read if you do happen to have the September issue of Civil Engineering magazine on yourself or with your company. So our next step in the process is we're working with a couple industrial partners to develop a field site that looks like spring is probably we're going to be injecting it into a pilot study. We want to look at the increased loads and frequency and what that does to the ballast substructure and maintenance requirements. Also interested in that sand spillage and being able to demonstrate the technology, because with sand spillage, it's one of those types of fouled ballasts that is relatively easy to inject polyurethane in to stabilize. So this is one of our possible field sites at an industrial sand facility in the Midwest. So you see on the right, obviously this track section has accumulated lots of fines, and this is what we're proposing to inject the technology in. And then what we would be doing is measuring the response to see how well this works. We are going through the process now of investigating we have a one site that we may be able to get to next spring and that we've already looked at, and one that we're proposing to look at, characterizing the subgrade and the subballast system using geophysical methods and dynamic cone as an example to characterize that substructure. So here you see in one of our proposed sections running a dynamic cone to be able to measure the strength as we go through the system. For the industrial sand site, we're proposing to eject in 2 layers, one layer in the subballast, immediately below the ballast section, so maybe 2 foot below the track section, and then another one deeper, maybe about 5-6 feet below. So in this system, we would be stabilizing the subballast and the subgrade itself, depending on how our field investigation goes, and we're looking for about a 60 linear foot injection zone. So this is where we're headed to the next phase of the project. We expect to measure less volumetric strain than the control section, decrease vertical deformation, thus a resistance to heavy axle loads, and decrease pressure on the subballast and subgrade. With these results in this demonstration, it'd be another tool in the toolbox per se to mitigate settlement and geometry issues and to reduce the frequency of maintenance events, which are the bane of many of the track supervisors and engineers out there. So just one quick plug before I turn off and await any questions you may have. I want to indicate that I'm a professor in several departments, and my primary affiliation is with engineering professional development. We run very popular and long-running courses across the rail industry. An example is Fundamentals of Rail Freight Terminals, Yards, and Intermodal Facilities that my colleague Dave Peterson programs. I program the geotechnical side of the business, foundation engineering, soil engineering for non-soils engineers, slope stability and landslides, and the like. So if you want to hear more about these continuing education programs, please, by all means, go to epd.wisc.edu and you can find more information. So with that, I'll back off, and over the last 5 to 10 minutes that we have, I'd be more than happy to take questions from the audience and listen to some of the response. Thank you.
Okay, thank you. So we had a few questions coming in, and again, this is Robert Armstead. You can submit your questions utilizing the toolbar of the webinar, and so please submit your questions there. So the first question is, what is the application process, and is it faster than new ballast application?
So the process is really, we haven't done it, but we anticipate being able to do a section of track, less than a half of a football long in a 1 or 2 day period, depending on the number of injection points and what we're trying to mitigate, either the subballast or if it's a substructure subgrade problem. The best scenario is, though, that once you inject the polymer, we get pretty close to full strength within about 15 minutes. So it is very much could be a strategic remediation process, especially applicable to bridge approaches, intersections with highway networks, frogs, and other crossings where we have intense loads and the like.
All right, great. Next question, how does polyurethane grout affect the free draining properties of the ballast? In other words, how does using polyurethane grout affect the permeability of the ballast?
So very good question, and the polyurethane stabilized ballast will be a relatively impermeable structure. So that can be a very good thing depending on where you are, in that the water is going to drain around it and not through it, because it is relatively impermeable to moisture. And so it will have to drain around the stabilized section.
Why does the sand spillage cause moisture retention? I think this is referring to the potential pilot project location.
Yeah, so the interesting thing with fines is the smaller the particle, the more surface charge there is, and more surface charge, the more you're going to retain moisture. And so, interesting enough, even fine to medium sand accumulates much more moisture than a clean, free-draining 3-inch ballast, and significantly more. So unlike conventional wisdom, where you would think that sand is going to drain just as well as ballast, it actually doesn't. And we have found, especially the fine sand for the natural gas fracking industry, retains a significant amount of moisture in the ballast substructure, and any moisture accumulation decreases the mechanical properties of that section and leads to increased plastic deformation.
Has the injection plan with volume been proposed for this on-site testing, specific to the geotechnical qualities of the given site?
So could you repeat that question one more time?
Certainly. It says, has the injection plan with volume been proposed for this on-site testing, specific to the geotechnical qualities of the given site?
Because of the site that we are proposing to go into the spring, is we are still moving to determine the subgrade characteristics and how foul the material is. We don't have the specific volumes of the chemistry that we're estimating quite yet, because we're still under that field investigation approach, and also to some degree because this technology has only been applied in a few places in the United States and more frequently in Europe, we'll be learning as we go about how much chemistry is needed per type of track. So we're still learning, and I can't fully answer that question. That's kind of where we are in the research.
Beyond routine rail inspection of the line, what additional investigation does URETEK need to determine the injection schedule?
For the injection schedule, we really need to know how tight the fouled section is. And so when I say how tight, is would the fouled section allow for permeation grouting, where the material can get through the fines and permeate that void structure, or if you're in the subgrade or a very dense fouled ballast, if you're going to be doing displacement grouting. So the biggest, in my view, the biggest important issue is kind of the fines and the structure of the material that you are trying to grout. So what type of soil it is, what type of ballast it is, and how much fines are fouled in it, and what type of fines they are, all are going to help answer that question of the type of injection strategy that would be implemented.
Can we use the polyurethane stabilized ballast in severe winter regions? How does it respond to temperature variations?
Another very good question. One of those graduate students that you saw on that list on the front page, half of his thesis was evaluating both freeze-thaw and wet-dry cycling on polyurethane stabilized ballast, both fouled ballast and clean ballast. And he found in that thesis that freeze-thaw cycles did not impact the mechanical properties of that stabilized section. And if you want more information about that, I can be happy to send that thesis to anybody out there. Actually, if anybody is interested in any of these papers that we publish, various theses, please contact me at jmtinjum, Tinjum, at wisc.edu, and I'd be more than happy to send you our journal papers and other documentation of these various research studies.
And I'm sure as many of you have seen, his email is actually on the PowerPoint slide in the presentation, so if you need to, you can find it there. Next question, what are concerns for polymer durability with regards to UV temperature and delamination with moisture and fines?
Another very good question, and I would actually put that question back to URETEK, who has used this technology for the past 25 years in pavement applications and the like. But in short, my theory is it's not going to have an impact because we're not proposing to inject right to the surface. So we should not have ultraviolet impact to the structure itself. We are proposing to inject probably at least 1 foot below the surface. As far as delamination and other types of impacts like that, in the laboratory, and I understand that the laboratory is not the field, is we did not see delamination at all going onwards of cycles of 500,000 cycles, and 500,000 cycles might represent 7 to 8 years of rail traffic. So we haven't seen it in the laboratory, but it's something that we would need to look at in field applications for long-term application.
Great. What are the advantages of the polyurethane section over a mud mat?
So I assume what you mean by a mud mat is just that a mud mat, if I'm thinking of this correctly, as the questioner has proposed, is something that you would install during construction of a new rail section and putting down a mud mat of low-strength concrete below the ballast. The primary difference would be is that polyurethane stabilized ballast could be done post construction, after 5 years of use, 10 years of use can be going in. But I do understand that some of my colleagues in the industry have proposed using asphalt or polyurethane stabilized layer at the bottom in rail construction to prevent piping of fines and moisture from the bottom. So a good question. The major difference is that polyurethane stabilization can occur, post, not just during the construction stage, but through the lifespan of the rail.
Okay, I do want to make sure that the question was addressed correctly. If I can, I'm going to unmute the questioner and see if it was done correctly. Kevin, are you available? Are you able to speak? Kevin Say? Okay, so potentially not. Mr. Say, if you did have any follow-up to that question, please submit it in the question section and we'll make sure that it's addressed. The next question is, what is the life expectancy of the product? What about cold weather climate?
The life expectancy, I see it lasting at least 10 years, but again, that's under laboratory controlled situations. What we really do need is to, get funding and more industrial partnerships to try this in the field so that we can answer those questions about longevity. In our modeling, and I understand that modeling is not real world, it's simulation of the real world, is we're modeling life expectancy of properly injected clean ballast, clean sub-ballast, is that there wouldn't need to be a remedial releveling for 10 years. Are we still live?
I'm sorry. I was reading away at a question. Let's try that again. Is this process applicable to addressing pumping associated with rigid pavements or for stabilizing weak soils and road construction projects?
The answer to that is a definite yes, even though that is not my particular area of applied research. That has been done for decades with this product for both with Department of Transportation, highway infrastructure, and also for airline pavement sections. So that this technology has been used extensively in the transportation industry in general. It's just that the applications in the rail industry are just evolving recently.
Great. Any other similar methods for stabilization, or is this a unique method?
It is a unique method in that it can be applied, post operation as a maintenance activity. Technologies that would have similar tenets as far as load distribution, control of water would be geosynthetics, between the subgrade and the subballast. And also some tracks have placed a pavement section, an asphalt section between the subgrade and the subballast during construction or during a major remediation. So this is fairly unique about how you can apply it, but there are other technologies that can also be applied to get some of the similar mechanical property and responses.
Thank you. Okay, so next question is, how much spread do you anticipate from the grout? If the spacing is 2 feet, won't you be creating, in effect, 2 impervious walls for any rainwater that falls between the 2 injection locations?
Very good question, and the spread is going to be controlled by the field operator based on that extensive experience and the touch that they have, because they can control the grout viscosity, they can control the injection pressure, understanding the grain size distribution and where they're injecting. So it can be controlled, but realize that the quality and the experience of your operator doing the injection very much comes into play. So this is part science and then part applied art in getting control of the spread of the injection.
Okay. Next question is, what is the expected service of life of a polyurethane injected ballast section?
So again, freeze thaw, dozens of cycles of freeze thaw that would represent I believe we represented it up to 10 winters in Wisconsin, had no significant deterioration in the mechanical properties of the stabilized material. Wet-dry cycles of similar nature also did not. And then we ran up to 1 million cycles of load, so 1 million train wheels hitting, representing, depending on the tonnage of that line, upwards of 10 years, and we did not, see significant decreases in the performance. Again, we haven't addressed that delamination issue in a field process yet. So again, my hypothesis is that the life expectancy would be at least 10 years.
Great. Any other similar methods for stabilization, or is this, oh, I'm sorry, this was asked earlier. Okay. Is there a way you can determine the spread of the poly material after field injection or confirmation that the target area was improved?
Yeah, there's two ways to do that. Is number one, or actually three ways. Number one is you're going to quantify the volume of chemistry being injected. So given a given porosity of your structure and how much chemistry is injected, you're going to get an idea of that spread. Secondly, you could go in there post-injection and tear a section apart, cut into the side of the track, and follow the tendency for where that polymer went. And third is what we're planning to do is measure the track stiffness pre-injection and post-injection. So really, ultimately, what we're looking for is improvement in the track modulus, the entire structure modulus as a whole, and that's what we're proposing for our field site, is to demonstrate performance by measuring track deformation over time post-injection.
Well, Dr. Tinjum, thank you very much for your time today. Greatly appreciate it. We actually still have even more questions, so we'll start to address some of those via email, just
Sure.
to honor everyone's time. But a few things. Do want to say, first of all, thank you, Dr. Tinjum. That was excellent. Judging by the questions, we're already over noon, so a lot of good feedback, and I'm sure you as well as ourselves will get requests for some of your paperwork, so we will reach out to get that. A couple just things in closing. We have done a few rail projects even before this. Testing has been done with the University of Wisconsin, so it's going to be very exciting to have a third-party verification. But a project and just a couple project profiles, I won't even go through these in depth for sake of time. But with a lot of the major rail lines where we've helped either their spurs or their main lines, this particular one here at the Amtrak where we lifted the rail 1.5 inches. You can see that picture in the center. Anytime a rail went over, it would displace water up through the top, and we injected our material to stabilize the soil, much as Dr. Tinjum talked, and then we're able to increase that bearing capacity. And so we have a variety of other project profiles we'd be more than happy to share with you and your team to help you on your next rail project. As mentioned before, we are doing monthly webinar series. Our next month will be December 11th, 11 a.m. Eastern. We will have Randy Post, who is a senior project engineer with Golder Associates, and we'll be talking about really some of the geotechnical aspects of polyurethane grout. You'll hear about one-part and two-part grouts, and so he will provide a report on a test that him and his team have done. So with that, thank you all very much for those questions we did not get answered. We will reach out to you individually. Also, you will be receiving a survey, so please give us feedback, as well as Dr. Tinjum, so we can improve, and then we'll also get your PDHs. So thanks, everybody. Greatly appreciate it. Have a great weekend, and